Good morning. My name is Tong-Yi Zhang, come from Shanghai University Maturetsunami Institute. Today, my presentation title is From Data to Knowledge, talk about data-driven discovery of formulas. Further, I would like to introduce the Center of Materials Informatics and Data Science. So this is really an interdisciplinary center with about 20 researchers, 5 from computer science, 7 from material science and engineer, and the rest from chemistry, physics, and so on. We have a very wide collaboration with the global materials data institutions. The center has received a lot of financial support from the Chinese central government and the Shanghai city government as well. So the materials database in Shanghai University is called Maturetsunami. So we do have a very fair infrastructure. So our policy is the data provider will hold the data copyright. The data provider will determine when and to whom the provided data will be shared. The Maturetsunami is really a fair data infrastructure for materials genomics. Currently, Maturetsunami covers more than 50 databases of ferrous metals and alloys, non-ferrous metals and alloys, metallic matrix composite, ceramics, ferroelectric materials, thermoelectric materials, ceramic coatings, fatigue, certification, and so on. So this is our materials genome website. So currently we are trying very hard to build up the English version of our database. So there are examples to show how my colleagues in China, they share their data with all the people. So now this is fractography. So it's provided by Professor Liu from South China University and Technology. So this is an interface cartography provided by Professor Zhang from Tsinghua University. Though this is animal fibers, those data are provided by Erdos company. So this is another data. Those data is talk about the solubility in alloys provided by Ningbo Institute of Materials Technology and Engineering. The Shanghai Research Institute of Materials, they also provide data on steels and alloys, on titanium alloys, on materials characterization data, on corrosion and protection data. The high throughput experiment data are provided by Shanghai Synchrotron Radiation Facility. Though the East China University of Science and Technology, they provide the failure analysis data. The Shanghai Institute of Ceramics, Chinese Academy of Science, they provide a lot of ceramic data and databases. They have their own database, but some data are installed in materials genome. Now we talk about how to, from data to gain knowledge, the knowledge from data. Now we talk about the data is really an input. Then we through machine learning model to gain knowledge. So once we gain the knowledge, we can explaining what happened. Once we gain the knowledge, we can predict what will be happened. Once we gain the knowledge, we can manage things that are happening. Now this is a very, very hard area. We call those a lot of automobiles aircraft, and also for cars. Learning actually can be done by individual human being, especially by genius, or and by machine. And here I take one of the example. It's about Newton's law. Newton's law is really come from the observation of the movement of the star. Okay. So then, of course, Newton is a genius. So they developed also calculus. Then they discovered Newton's law. So in my personal view, the development of nature science is a continuous and endless progress that human beings observe nature behaviors, develop learning models, and then gain knowledge. And usually those knowledge are expressed by formula. So in data-driven formula discovery, so the key issue is we have to find the effect of the most important variables and factors. So nearly all the formula are data-driven discovered. So now here we take some examples. The Kepler's law, the Newton's law, the Hooke's law, and also equations, a lot of equations of state. That is widely used in material science and engineering. So now, currently we separate the discovery into two approaches. One we call data-driven. From time to time, people call those phenomenological formulas. Another we call that is based on physical argument and already known the formulas, then to derive those equations. So this we call the deduction. This side we call induction. Now our approach is we want to emphasize very much to combine the experimental knowledge-based formula discovery with this data-driven formula discovery. We have to combine them together. So here, I take another example. It's talk about the Paris law. Paris law for fatigue chronic growth. So Paris law is very, very important because most of the failure engineer in your industry is caused by fatigue. Paris law, Paris is based on those data. He developed this Paris law. It's very much simple. You can see that the equation is very much simple. So this Paris law is widely used in academia and also in industry to predict fatigue life for our safety. So Paris law is purely a data-driven formula, and so far no theoretical derivation has been yet published. Another famous equation, especially in the metal industry, is the Herpetic equation. The Herpetic equation is about the grain size dependent strings. So it is amazing how if you know they have a relationship, but how do you know those the strings is related in the grain size, the diameter, okay, the D, in such kind of form. So they are really come from purely experimental data. But the things is different from Paris law. The Herpetic equation now has been derived from different theoretical model. the people can set up a different theoretical model, then derive this Herpetic equation, get the same Herpetic equation, but the model somehow are different. So now talk about machine learning. The machine learning, we have input data, then we have output data. The output variable usually we call is responses. That is the input data. Now the system in machine learning, they treat this system like it's a gold black box. Because there, the information is not sufficient, and also inside here, we have a lot of unknown variables. So those unknown variable, they will cause an intrinsic error. Those intrinsic error could be very, very large. For example, in our stock market. But in our stock market, you cannot get enough information. So those errors could be 200%. Okay? So you want to make money from stock market, that is very, very difficult. However, in our science and engineering, we can improve our experimental setup, the software and hardware. We also can improve our computation algorithm and our computation method to make our experiment more accurate, or computation more accurate. So this one can get smaller and smaller. So in machine learning, we have to do an area analysis. They have in this one, they have two very, very important things in machine learning. One is the feature, another is the feature space. I usually call feature space is a search space because you want to predict something. So by set up features and also feature space, you will determine another two areas. One we call bias, another we call variance. A best machine learning model is to make those those two parts, their sum up. The two parts, their area, get the lowest one. So the total area have three parts. Keep that in mind. The intrinsic area has to improve our original data. Okay, that's whether you come from experimental or you come from computation. You have to make that area as small as possible. But in machine learning, what we can do is to reduce the bias and the variance errors. So usually a data set is divided in two subsets. Some people say divided into three subsets. So here I just talk about these two subsets. One we call training set, another we call testing set. So keep that in mind. Now we are handled with data. So that means if we want to use some formula or to use some things to fit our data, the solution is not unique. So here is an example. Those is the data, what we know, but you can use a different model or different machine learning model to fit those data. So you want your model have more prediction power, much stronger prediction power. So however, if you make your model very complicated, then your area for your training data set, when doing that training, the area will get smaller and smaller. However, if you testing your model, so the area will reach a minimum and then increase as your model get complex and complex. So therefore, if your model is too complex, then your model will lose the prediction power. So now we have also face a bigger a challenge. We have major difficulties in our materials data. So the data usually is very small, so especially for experimental data. So all the data has high dimension, so very, very high dimension. And a lot of data has a bigger noise. Okay, that is maybe caused by some intrinsic nature of the materials. Okay, they have when make that, they have a very big noise. So that is a major difficulty. Small data, big noise, high dimension. It's a very, very big challenge. So we want to our formula as simple as possible. But however, so we will handle in mathematics a Chopin sparsity. Okay, so there we think that for all things being equal, the simplest solution tends to be the best one. We are trying to get one. How to get one? We have to catch the most important variables and also to catch the key relationship among them, among those most important variables. That is based on your, what's your goal, okay? You have to determine which one is more important. So in our new build-up algorithm, we fully utilize our domain knowledge. We utilize our domain knowledge with the dimension analysis to normalize the input and the output variables. And also, during which we have to take care, okay, to watch the magnitude of the dimensionless variable. Those magnitude should be maintained within a certain region. If this is a magnitude have a bigger difference, then we are making your calculation much more difficult. So now further that show that after that we have those dimensionless variable as a further input. Then we use that as a power. We can put those power minus 2, minus 1, 1, or 0 is a constant. We have put it also there. So 1, 2, 3, and so on. Do the first we will combine them together from the first those 1, the stack, the further combination. Then we have always have some constant. So therefore we have to put a 1 to represent this basis of this is a constant. Then we combine them together. We will get a feature block candidates. So now we have to build up some rule. This rule, of course, can say very much is adjustable. Okay, you can put your rule. In our current rule, we said in one feature block, so the number of dimensionless variables is usually not larger than 3. So in one feature of the blocks, the absolute sum of power is usually not larger than 5. Why you want to make those rules? Is want to make our computation is feasible. So now after we use this rule, we will get features is blocks. So we get those one. So then we get those features blocks, then we put our function. We have a function size. We have to put more function here. This is for example exponential, log, sine, cosine, and so on. Okay. Then when we add those functions, then we get a lot of we call each of these features. We get this feature. We build up, we call feature space. So here the n means in the feature space, how many features are there? Okay, how many features? Then in next step, we have select p features from the feature space by combination. So keep that in mind. During this feature selection, okay, select this p feature, we have to keep the integrating output variable must be including in the p features. So then we use that p features form a linear equation with this to be determined constant, coefficient, to be. Though here in our those current practice, we like that the numbers of the term of the equation is usually not larger than 6. Maybe you can think it's maybe 5, 7, or even higher. But we think 6 is very complex enough for most tasks as shown in our the following test cases. Then to find this formula, it turns to be to solve this, to determine the constant coefficient, to do that. So how to do that? Of course, a lot of people try to use the evolutionary competition. So that is a well-developed algorithm. So you just follow that of nature's selection, survival of the fittest. So what we wrote is our code in parallel with a very new computer language, Jola. The Jola actually is licensed at MIT. There is the website. Some interesting people, you may download this Jola. This is a language, from this website. So our search procedure is if our potential formula candidate is less than 10 to 9, we just do a exhaustive search. We just search that. Then otherwise, we will use this evolutionary computation. Maybe we use the L1. Maybe use this we just mentioned that all those evolutionary computation algorithm. Then through this, we will reduce this M formula candidates to the top best key formulas. Then here, with that, how we judge that, we use that the minimum average, the relative absolute error, we call that AE, is a definition is given here. That is to judge whether your formula are good or not good, to evaluate the formula. Then we will conduct second calculations of a potential formula, solve each of the variable in the formula by taking other variables as independent variable. That means your original function could be changed to as an individual variable. Then originally individual variable could be a function, to do the cyclical calculation. In the cyclical calculation, a potential formula, 90% of the area of the calculation should be smaller than the precise threshold. For example, we said that is like 2%. So then with that, we go to the next step. We are either we found our solution, or we recommend our solution, or we will suggest that you need more data. Maybe your data not enough. So in this step, we have to compare whether this formula is a very complexity or with accuracy, and also how to count this. We have others, those 3 methods are shown here. 3 methods. Now the following I will give you some showcase or example testing case. The testing one is like this function, v equals sine x plus sine y squared. Like you say, x there is in this region from 0 to 1, y also in this region. Then we randomly generate 50 data. The noise there is either by is a random number. Here with their duration, standard duration, 5% of the absolute value of z. So now the total feature, feature is that I have 65. Then we select those potential feature feature is a candidates from there, from those is a conditional number, okay, we are searching for this. So now we use that, okay, what is our result? Let's see that. So here, show that if without is a noise, okay, so we will find that is this, keep that this is the 9, 12, 65 is actually this TI. TI that is in each of the feature space is a number, we have showed that before. So now from there we can find that right away we can find what from this simplest one, the best is the feature, we have found that. So now from the histograph is a plot, we also can find this one. Without the noise, that's very much simple, like the case. Then, if we put some noise here, then we will find, okay, from there, we will find some, those potential candidates, okay? They give you, the formula is give you, they are contain, it's a 6 term, because we are, it's all 6 term, but in this side, we consider it's only 3, 3, 3. Then we have to combine the simplest ones we mentioned that is the best. So we are trying to find that this is the best one, okay? Not just compare, this is the accuracy, okay? We are trying to find the simplest one. So from there, with the noise, we suggest that is data, the formula will be very close as our input data. You can compare here. There is 1, but here is 0.99. So here is 1, but here is 1.01. Okay, it's very close because that is caused by noise. Okay, because when the noise, also keep that in mind. Our data is only 50 data. It's not really big data. So we summarize all those. Is the case 1. We can get this conclusion. Without noise, we can recover our original that formula right away. Okay, we can find that. With noise, they always have some errors here. And we can find what's here show our AE, how large it is. Okay. Now for case 2, this case 2 is a little bit more complex formula, as we showed here. It's a 2 log function, and also here. We also randomly generate 50 data. Okay. So the noise also added by assuming the noise form is a normal distribution. So here, so we have a totally this n potential that is a feature. In the feature space, it's 136. Then we take that. Then from that, without this noise, we can recover our those equations right away. Okay. But the base is a noise. Then we have get that equation is more complex. It's derived from the original one, but the area, the AE, is a little bit over 2%. So for case 3, case 3 is the case that is suggested by my colleague in our computer science engineer. They said they always use this equation to check that. So we also randomly generate 50 data, but we put a constraint when we generate this data, either this variable or x and y, they form this normal distribution. They have the derivation 10. That means we generate x and y from -10 to +10. Okay. Now we have a totally in our feature space have 65 features. So now we do that without the noise. We can find this equation right away. With that is a noise, we still, even noise scale is not very large, we still can find that, okay, this equation. But when the noise got bigger and bigger, so now we cannot find, okay? We have found we just approximate equations. But however, if this data is still 50 data, if we like this is a variable, there x and y, they ranged from minus 100 to positive 100 in this region. We get that the feature space is 65. We do all these same things. Then we are found, okay, there is no, for this term, we can find this is a cosine x, but for these those two terms, we cannot find. What's the reason? The reason, if we carefully check that, we will find that most of this is a value x outside the region from minus 1 to positive 1. But we all know the cosine x is always located in that region. Okay, so we have to keep that in mind. Okay. So now my concluding remarks is though enough reliable data and the necessary and essential condition. So now my concluding remarks is though enough reliable data and the necessary and essential condition to mature informatics, we have to encourage our data, our colleagues, okay, international-wide colleagues, to share their data with us. So from data to knowledge formula is a jump from quantity to quality. So knowledge formula from data is achieved by learning of mankind, especially genius, like all of you, and machine learning. We have to combine them together. Thank you for your attention. Any questions are welcome.